VLSos here. This is a video lesson on infinite geometric series. Let's imagine a contextual situation, a real-world situation. We're lying on the floor and we have a ball and we throw it up in the air. And the ball reaches a height of 10 feet and comes back down. But we don't catch it, we allow it to bounce. The ball bounces up, but not as high as before, and comes back down and bounces again and again and again. The initial height was 10 feet on the first throw or bounce. And the rule for finding the height of the next bounce is that it is 60% of the previous. This is enough information to generate a table where we compare the bounce number to the height or distance traveled by the ball. So on bounce number 1, or the first toss of the ball, it reaches a height of 10, but if we want our table to reflect the total distance traveled, we have to double it because the ball comes back down before bouncing. So in this table, G sub n will stand for the distance traveled in that bounce, and the first bounce has a distance of 20 feet. The second bounce will have a distance that is 60% of that, or 0.6 times 20 is 12. And the third bounce will have 0.6 times 12, which is 7.2. And we can carry this forward. If we take a look at this, we think we've generated a sequence of numbers. And the nature of this sequence is that it is geometric. Because we're multiplying by the same 0.6 each time, that is the constant ratio of a geometric sequence. R is equal to 0.6. And if we have a geometric sequence, we can take advantage of the equations that help us with geometric sequences and series. In this case, I'm going to remind us that the value of the nth term of a geometric sequence or series, and I could have used a t, but I'm going to use a g to stand for it in this case because I know it's geometric, is equal to the value of the initial term times the constant ratio to the n minus 1. So what if I wanted to use this situation and think, how far does the ball travel in the first 15 bounces? I know that if this is a geometric sequence or series, then I can sum the first n number of terms with the formula S sub n is equal to the constant ratio times the nth value of the nth term minus the value of the initial term over the constant ratio minus 1, which is a pretty sophisticated formula, but if we wanted to use, we could use it to find the total distance traveled in the first 15 bounces. And that means that I would be choosing an n value of 15, and I would need to know, if I was to use the formula, the value of the initial term, which is 20, and the value of the 15th term, which I'll need to calculate with this formula from before. The value of the 15th term is going to be the value of the initial term times the constant ratio of 0.6 to the n minus 1, or in this case, 14th. Using a calculator, 0.6 to the 14th and then times 20 is going to give us an approximate value of 0.016 feet. That's very small, but if we can visualize a ball bouncing, the 15th bounce is going to be very small, maybe even undetectable. In our table, we could put an n value of 15 and the corresponding distance that the ball traveled, 0.016. Now we're ready to use this formula to calculate the sum of the first 15 terms, or the total distance traveled by the ball in 15 bounces. It's going to be the constant ratio of 0.6 times the value of the 15th term, which we calculated 0.016, minus the value of the initial term, 20, all divided by the constant ratio of 0.6 minus 1. Using a calculator, 0.6 times 0.016 minus 20 is negative 19.991, and then we're dividing by a negative 0.4. We expect a distance to be positive, and it will be because these negatives are going to cancel out, giving us an approximate distance traveled of 49.976 feet. That's the path of the ball in 15 bounces. But it leads to wondering, what is the total distance traveled by the ball? Well, in a real-world situation, if we threw a ball up and saw it bounce 15 times, we might not be able to attack the height of that last bounce. And at some point, friction and the nature of our world is going to take over and the ball will indeed stop. But mathematically, this sequence carries out to infinity. We'll always have a bounce height, even if we're trying to find the height of the ball 10,000 bounces down the road. That height might be minuscule, but it'll be greater than 0 at any value n. So what does it mean to find the total of the distance traveled by the ball? Does the ball travel a distance of infinity? Does it keep bouncing forever and always add to the total distance that it traveled and never stop? Well, we could ask this question using this formula, but we would run into trouble. A lot can be said about infinity, and we'll study the mathematics about have to do with infinity in pre-calculus and calculus. But for now, we look at this formula that requires the value of g sub n, the last term. There is no last term when we consider n to be infinite. So we can't use this formula because we literally can't calculate the value of the infinite term. So we can approach it with sigma notation. If we did, sigma is used to produce a sum. It has a starting value. In this case, n would be equal to 1, and it would go up to not a final value, but it would keep on going to infinity. And what we're adding together is the distance that a ball travels, or how we generate the terms of the geometric series, g sub 1 times r to the n minus 1. But again, thinking of this sigma notation as a way to sum up all of the distances traveled in all of the bounces, we still have the concept of the final value that we use is infinity. Infinity isn't a value, so we can't use it as such. Thankfully, mathematicians that have used calculus, which is beyond the scope of this course, have found that this sum can be represented by a formula that will produce the sum of an infinite number of terms added together, as long as the terms are geometric and as long as the rule for the geometric series has a r or constant ratio between 0 and 1. That formula is very elegant. To find the sum of an infinite number of terms of a geometric series, we take the value of the initial term and divide by 1 minus r. That's it. So in this case, the sum of the entire series of this ball is 20 divided by 1 minus 0.6, or 20 divided by 0.4, which is exactly equal to 50 feet. The results we can compare. 15 bounces, just a little bit shy of a total distance of 50 feet. Infinite number of bounces, exactly 50 feet. The sum of an infinite number of terms of a geometric series is not infinity. It's a finite value found by this formula. As long as the constant ratio is between 0 and 1. Why does it have to be between 0 and 1? Well, think about the ball bouncing situation. The term values gradually go to no height. If we had a ball bouncing that became higher and higher and higher each time, then we'd be adding an infinite number of numbers that were growing and growing, but in that case, we wouldn't have an R value between 0 and 1. We'd have to have an R value greater than 1 if the height was continuing to grow. In that case, to use this formula, R must be between 0 and 1.